Yes, sir. Thank you.
Yeah. Okay. So the topics which we are going to cover in fluid mechanics is fluid properties, fluid statics, manometer, buoyancy, forces on submerged bodies, stability of floating bodies, control volume analysis of mass, momentum, and energy, then fluid acceleration, differential equations of continuity and momentum, and then Bernoulli's equation, dimensional analysis, viscous flow of incompressible fluids, boundary layer theory, and then elementary turbulent flow only. Will not go much in deep for this turbulent flow, only basics will cover in that. Then flow through pipes, and then head losses in pipe bands and fittings. Okay. Now the books which you can refer is F.M. White or Somem Biswas for numerical. This you can refer for GATE exam, but particularly for HL exam, see if you have attempted last year, then you must be knowing that only conceptual type of question they are asking. You can guess this thing on the basis of time and question ratio also. Like you have 100 technical questions and corresponding time available for that is approximately 100 minutes only, 1 minute for one question. So they cannot ask some lengthy question or numerical questions. Basically they will ask conceptual type of question only. So I will be covering, see, the way I will proceed is that first I will teach you this basic concepts, okay, and then we'll try to solve many numericals, conceptual numericals, or not numericals, sorry, uh, this conceptual, this objective questions, and few numericals based on those topics, okay. But for GATE exam, you can prefer FM White, Som Biswas, and Senjal. And Som Biswas numericals are must for GATE exam. Okay, you can go through previous year questions of GATE, and you will find some of the questions they have directly asked from the unsolved question of Som Biswas, or few solved examples also, but mostly they have asked unsolved questions of Som Viswas. Okay, so for GATE point of view, this book is numerical of this book is very good. For concept, you can refer Senjal Simbala or and FM White. So shall I just revise and start solving numericals? Yes, you can do if you have. Anyway, I will take many numericals, so you can stay in the class and solve those numericals. Naveen. Okay, so I will not go much in deep. I will stick to basic concepts only, and then we'll try to solve as many conceptual questions. Okay, so we'll start from physical states of matter. So basically we divide state of matter in solid, liquid, and gas. We divide it as solid, liquid, and gas, and there is a plasma state also that is not covered in this syllabus. So these three states only will cover, and basically we are going to study about what fluid mechanics. So okay, initially this mechanics itself, if you see, mechanics, which is a physical science that deals with both stationary and moving bodies under influence of force. So you see this mechanics is further divided into this rigid body mechanics, okay, then deformable body mechanics, and then fluid mechanics. If you apply this mechanics concept on fluid, this is fluid mechanics, okay. And if you study this deformable body mechanics, okay, this comes like your strength of material or mechanics of solid, what we study. So there that topic comes under this deformable body mechanics, because there is the deformation of body occurs, and there is a stress or strain because of that it induces in that body. And in rigid body mechanics, there is no deformation of body, and this we further divide into statics, kinematics, and dynamics, what you might be studying in our this mm, uh, engineering mechanics class. Okay, so basically we are covering this part now. Okay, fluid mechanics, which will further divide as fluid statics, fluid kinematics, and then fluid dynamics. Okay, like this will go. So few basic things we'll just quickly cover. Like for solid, it holds its own shape. Okay, it has fixed volume. It has fixed volume. Okay, and the molecules are arranged in regular repeating pattern, and they are held firmly in place but can vibrate within their limited area. So this is the basic uh, thing for our solid. Okay, now when it comes to liquid, the important thing is that the liquid forms free surface. Okay, the liquid forms free surface. See, this both thing, this liquid and gas, both are fluid. Okay, but this gas, which is a fluid, does not form free surface, but this liquid forms a free surface. Okay, this is the one basic difference between these two. Now, next is this liquid. If you compare the shape, this holds its own shape, the solid, but liquid takes the shape of the container, and gas also takes the shape of the container. Now, coming to the comparison of volume, you see these two are having fixed volume. Solid and liquid, they have fixed volume. But for gas, it will fill completely the container. Okay, so its volume can be calculated with the help of the volume of the container itself. Okay, and this does not form free surface, this will have free surface. And then comes to uh, differentiation based of molecule, distance of the molecules. So you see molecules take means that make up a liquid flow easily around one another, but in case of gas, it flies in all direction. Okay, it flies in all direction and with greater speed here. Okay, so the attractive force between these two molecules in case of gases are negligible, insignificant. But here, although they are apart compared to our solid, but still this attractive forces between these two molecules, here these two molecules are significant in case of liquid, but in case of gas, this force of attraction is insignificant. So this is the basic differences here. Okay, now next is uh, the topics which we are going to cover is further divided as already stated. It will be fluid mechanics. Under this we'll study Pascal's law, pressure measurement device, hydrostatic forces on submerged body and buoyancy, and then fluid kinematics. Under this, streamline, streak line, path line, all these things will be covering. Okay. Okay, so now see today uh, we have target of solving at least 100 MCQs. Okay, so I will try to cover up to the properties of fluid, and based on that, we'll try to solve 100 MCQs. So just uh, stay and just try to understand the basic definitions of these properties and definition of fluids and the differences between the liquid, gas, vapor, all these things, because here only they will try to twist and give you that twisted thing in that option, which will be little bit confusing for you. Okay, so we'll try to solve as many as MCQ for that. Okay, so first we'll start with the definition of fluid. So what is fluid? So fluid is a substance which is capable of flowing. Fluid is a substance which is capable of flowing. Solid cannot flow, no. Liquid, here liquid or a fluid is capable of flowing. Now, it is a substance which deforms continuously when subjected to external shearing force. See, both the lines are very important here. They can make objective question based on this also. Like they can give means fluid can continuously deform when subjected to shearing force. It will not deform when subjected to shearing force. It can resist to shearing force. It cannot resist shearing force. Like that, they can ask uh, this MCQ. Okay, so that's why we should be very careful while reading these definitions. This is more important in terms of your HL exam. If it comes to gate exam, there we need to focus much on our numericals, our this uh, equations and numericals, but here the concept part is more important. Okay, so this too, fluid is capable of flowing and it is a substance which deforms continuously when subjected to external shearing force. Okay, now this fluid can be classified as liquid, as a gas, as a vapor. Okay, now what is the difference between this gas and vapor? What is the difference? Can anyone tell? What is the difference? Okay, it may take time for you to type. You can write. By that time I will just try to explain you, uh, so that we can save some time. So here you see liquid which possesses a definite and it is incompressible. Okay, liquid possesses definite volume and it is incompressible. First thing, liquid is incompressible and it forms free surface. This 2 point you need to focus here. It is incompressible and it forms free surface. When it comes to gas, it has no definite volume and it is compressible and it does not form free surface. Okay, now when it comes to vapor, see, vapor is a gas only whose temperature and pressure are such that it is very near to saturated liquid state. Okay, that means if you remember the plot from thermodynamics, let's say TS plot. Okay, and if I make this constant pressure line, so here we call this as vapor. This is vapor. Okay, this state. But if you go far away from this saturated curve, this is saturated vapor curve, this is saturated liquid curve. Now if I draw this constant pressure line, if you take the state point which is near to this saturated vapor curve, then this is your this is known as vapor, gas, which is a vapor. But if you go far away from this vapor form, then this we call as gas. Okay, and uh, in gas power cycle, on when you draw this TS PV curves, there we do not draw this vapor dome, this what we call as vapor dome, because the gas state is very far from this saturation state. Okay, but in case of vapor power cycle, we draw this saturation curve and then we draw this processes here. Okay, so why this thing called as this gas is known as vapor? Because if you extract the amount of energy from here, it will condense, some of the vapor will condense into liquid. But in case of gas which is far away from this saturated state, which is far away from this saturated state, if you extract a small amount of energy from here, it will not convert into your liquid. It will, its temperature and pressure will reduce, change of state will happen, but condensation will not happen. But when you are near to your this thing, uh, your saturation state, if you extract a small amount of energy, some of the condensation, some of the vapor can condense into liquid. Okay, so this is the basic difference between your gas and vapor. I hope I have explained this thing. Okay, mostly people have answered. Now comes to understand the property of viscosity. To understand the property of viscosity, first we'll try to compare the sample of solid and liquid. So if you apply a shear stress, let's shear force over the, let's say this is a solid sample and this is held it firmly like here, like this, and this can move in this direction. If I apply a tangential force like this, and if I apply a same tangential force on a fluid sample, what happens? This will deform. You see a deformation angle is formed here. Deformation angle you can see here, gamma. Okay, and this will remain constant, and if you further apply the force, it may break, but this will remain constant. After some time it will remain constant, it will not change. If you further apply the force, it will break, the solid will break. But in case of liquid, what happens? This will continuously increase. You see gamma 1 is lesser than gamma 2, and if you further apply the force, it will further deform. So what happens when you apply a shear stress? Now liquid continuously deforms. And now here only the concept of shear strain, what you must have studied in your solid mechanics, that the shear strain, the deformation angle, what you can see here, is given by tan gamma. You see this is right angle triangle will form here. So you can see this is delta x, this is delta y, this height. So tan gamma can be written as delta x by delta y, and we know this deformation will be very less, so we can write tan gamma as gamma only. And so we can write this this ratio is equivalent to gamma. And also we have studied in solid mechanics that shear stress is directly proportional to shear strain. Okay, here it is shear strain, but when it comes to liquid, it is rate of shear strain. Okay, this is the basic difference. Why? Because with time this angle is not changing in case of solid, this angle is constant, but this angle is changing with respect to time continuously in case of liquid. Okay, so this is tau. Shear stress is directly proportional to strain in case of solid mechanics, and to remove this proportionality we introduce this constant, which is your modulus of rigidity. So tau is equals to g gamma. Okay, now we'll try to compare this equation with our fluid equation. You see this is shear stress, this is shear strain, and this is one constant, which is what? Your modulus of rigidity. Modulus of rigidity means it will, this property will help to avoid the deformation happening here. Okay, similarly we'll have shear stress in case of fluid also, shear strain or in case of this fluid also, but there will be rate of shear strain, not only shear strain, it will be rate of shear strain. Okay, and then we'll have one constant also here, a proportionality constant. So let's see what it is. So in case of our this fluid, shear stress is directly proportional to what? Rate of shear strain. This derivation I will not go into this derivation. because you can refer book, but that is not much important in terms of your HL exam. What is more important, there only I will focus, okay, because in less time we have to cover more. So you see, shear stress is directly proportional to rate of shear strain. This is one thing. And if you want to remove this proportionality, we'll have to introduce this constant, and this constant is mu, which is known as viscosity. There it was, shear stress is equals to G gamma. So this is shear stress, this is shear strain, and this is modulus of rigidity. So this is a resistance for deformation. Okay, this property is resistance for deformation. Here, in case of liquid, if you see, this is shear stress, this is rate of shear strain, and this constant is resistance to flow. Here it is resistance to deformation. Here, as the fluid continuously deforms, so and as it is deforming, it starts flowing, and the resistance to flow is given by this property, which is viscosity. Okay, is it clear to everyone? Okay, now this same thing, this d gamma by dt, which is rate of shear strain, with mathematical means this manipulation, we can derive that this d gamma by dt is equivalent to your velocity gradient du by dy. Okay, du by dy. So this shear stress can also be written as tau mu du by dy. Initially, we did with derivation, we'll get rate of shear strain. This rate of shear strain can be written as du by dy, and this du by dy can be replaced here in this equation, and we can have tau equals to mu du by dy. So this is velocity gradient. Okay. So they can ask here that rate of shear stress is directly proportional to shear strain, rate of shear strain, or velocity gradient in transverse direction, in flow direction. All those options can come. Okay. Okay. So what is your viscosity? I have explained. Okay. Basic thing I have explained. It is basically the resistance between two molecules, resistance for flow, like this molecule which is in touch of this solid plate will not move. So this, because of what? No slip boundary condition. At the surface will have no slip boundary condition, so this molecule will not move. Okay, this will have relative zero velocity with this bottom plate, okay, or solid plate. Now the molecule which is above this one, or we can consider this layer will try to glide over this one. So this will try to stop this layer, or this layer will try to pull this layer. Okay, and again above this layer, this will try to move in this direction, and this will try to pull back this layer in this direction. And because of this only, a velocity gradient in this direction exists. So velocity at this point will be zero, and a velocity at this point will be maximum. Okay, so this viscosity, or absolute viscosity of fluid, or dynamic viscosity, either one of the name can be there in the option. So dynamic or absolute viscosity of a fluid is measure of internal fluid friction which causes resistance to flow. Okay, and what is the reason for this viscosity? So the reason of viscosity is two things. It is primarily due to cohesion force. In case of liquid, it is primarily due to cohesion force. Cohesion force is means attractive forces among the same type of molecules, same category of molecules. And another reason is molecular momentum exchange between fluid layers. So what happens, some molecule is here, some molecule is here, this is moving with, let's say, 10 units, and this is moving with, let's say, 8 units. So what will happen if this molecules move in this direction and enter in this layer? Obviously what will happen, this molecules, it will transfer its momentum to this layer, and its velocity will reduce. Some of the means there will be a bit increase of velocity in this layer, but as this molecule has transferred from here to here, which is having higher velocity, the velocity of this layer will increase a bit. Okay, so overall of you see, it is stopping, this layer is stopping this molecule from moving in forward direction, and that is how it is creating a resistance for flow in terms of what, momentum exchange. Even it happens like in your gases, this thing generally happens because the molecules are far away. So here, if let's say here it is the molecule is having very high velocity, but as it is very free to move, in case of our gas, so this can move to this layer, this can move to this layer, and again what happens, this velocity of this molecule will reduce when it happens enters this layer. Okay, and hence a resistance is offered for that molecule. So this is what happens in case of molecular momentum exchange. Okay, so the two things which is responsible for viscosity is cohesion force and molecular momentum exchange. Okay, now quickly we can see the unit of this dynamic viscosity is poise. Okay, and the relations between poise and Pascal second. One or more unit in SI unit is Pascal second. In CGS unit it is poise. So one poise is 0.1 Pascal second. The relation you can remember, 1 centipoise is 10 to power minus 2 poise. Now there is one more property which is kinematic viscosity, and this is given as dynamic viscosity divided by density. And this viscosity actually helps us in the definition of Reynolds number, because if you see, Reynolds number is rho v mu by rho v d, any hydraulic diameter, by mu. Okay, so you see this ratio, it is coming here. Okay, so it helps us in, when I will teach this Reynolds number, there I will explain this kinematic viscosity, the physical significance of kinematic viscosity. There I will tell you. But right now you can see here the importance of this kinematic viscosity. Just like that, we are not studying. It has physical significance, and it is given as dynamic viscosity by density, which you can see here. In Reynolds number, you will see this ratio. Okay. And the unit of kinematic viscosity is meter square per second, and its CGS unit is Stoke. Here it is poise, it is, here it is Stoke. Okay, now as we have studied that viscosity varies with temperature, means viscosity actually depends upon molecular cohesive force and molecular momentum transfer. Now these two things changes with temperature. Okay, it is affected with the temperature, and hence the viscosity is affected with temperature. So the variation of viscosity with temperature we are going to see. So in case of, you see, in case of liquid, if you see, this is a liquid sample and this is a gas sample here. So in case of liquid, the molecules are nearby and the attractive forces are significant here. In case of gas, the molecules are far away, so the attractive forces are not significant, insignificant here. So the thing which is dominating in case of liquid, is the cohesive force, and the thing which is dominating in case of gas is the molecular momentum transfer. Okay, so when you increase the temperature, what happens, the cohesive force between these two molecule what happens? It will reduce, and if it is reducing, so the viscosity will reduce. Okay, so with increase in temperature, there is a decrease in viscosity for what? Liquid. Why? Because if you increase the temperature, there is a decrease in cohesive force between the molecules of liquid. Now when it comes to gases, when you increase the temperature, the velocity of molecule increases. Kinetic theory of gases, if you remember, from there we can explain that the velocity of this molecule will increase, and if the velocity is increasing, the momentum increases, and if momentum increases, there will be more transfer of momentum, and hence the viscosity affected accordingly. So increase in temperature causes a increase in viscosity of gas. Okay, so you can notice the difference. Increase in temperature causes decrease in viscosity of liquid, but increase in temperature causes increase in viscosity of gases. Reason behind this is, here it is due to molecular cohesive force in case of liquid, but in case of gases it is due to molecular momentum transfer. Okay, so this two difference you should note. Is it clear? Okay, so next we'll see is Newton's law of viscosity. So whatever we have studied in last slide, that shear stress is directly proportional to rate of shear strain. So either this d gamma by dt, gamma is that angle, or shear stress is directly proportional to velocity gradient in transfer direction, in y direction. So tau is directly proportional to du by dy. Okay, and if you remove this proportionality, we get this viscosity. So this relation tells you that tau is linearly depending on rate of shear strain or velocity gradient. You see, if I plot in y-axis, if I keep this tau, and in x-axis if I keep this du by dy, this is y and this is x, so it is y equals to mx only graph. So this is a linear graph. So what Newton's law of viscosity tells is that shear stress of a fluid element layer, shear stress of fluid element layer, because viscosity is noticeable where? Between the two layers. When two layers are moving with different velocity, between this two layer only you will see the viscosity. There only viscosity happens, because it is a resistance to flow, no? So like in solid, what happens? This is let's say a ground, and if you have a box here, and if you are moving here, interface between this two, this box and the ground, this there is this interface. Here only you can see that friction, the resistance in this direction. Okay, so here in case of solid, what happens? This complete box is a single unit, but in case of liquid, what happens? All layers are moving, all different layers are moving. So in between all the layers, you can notice this viscosity. Okay, which is a resistance. Okay, so resistance to flow. So this Newton's law of viscosity tells you that shear stress on a fluid element layer, okay, shear stress on a fluid element layer is directly proportional to rate of shear strain, and this is what Newtonian fluid, this is the fluid which follows this law, the fluid which follows this law is called as Newtonian fluid. So which follows this linear behavior is your Newtonian fluid. If it is not following this linear behavior or Newtonian fluid behavior, we'll call that as non-Newtonian fluid. Okay, so if we have non-linear behavior also, then we should have an equation for that. Like here we have one equation which shows a linear behavior. So we should have an equation which shows non-linear behavior for non-Newtonian fluid. So we have that equation. Okay. So you see, for Newtonian fluid, we have this relation. For non-Newtonian fluid, we have a general equation, which obviously will be a y-axis here. This, see, in y-axis will have tau. In x-axis will have du by dy. So what a general equation we can form from here is y is equals to m x to power some constant, okay, plus some constant, another constant. This is how we can form a general equation, okay. And depending upon this power, it can be any curve, any curve. So this is how we can write a general equation. So here also you see we have a general equation. In case of y-axis we have shear stress. In case of x, in place of x we have du by dy, velocity gradient or rate of shear strain, and then this m, then power n, and this shear stress, yield shear stress is there, that I will introduce later. So this one constant is there, okay. So, and if you want to see the slope, like if you compare this equation with y equals to mx, the slope is what? Slope is what here? What is the slope for this curve? It is mu, which is a viscosity. A viscosity of fluid represents the slope, okay, here. Similarly, in general equation, if you want some viscosity, which we call as apparent viscosity, what you will have to do, you will have to separate one of the x from here. So this is the x, okay. Now the remaining part, m, some constant multiplied by du by dy to power n minus 1. So here the slope is m du by dy. It is dependent, it's not exactly this as the slope. Here I want to show you that the slope is dependent. Slope is dependent upon du by dy. The slope is dependent upon x itself. Here the slope is constant, which is the viscosity, but here the slope is not constant, so viscosity is not constant. So this is one more difference you can note here, that in case of Newtonian fluid, the viscosity is constant. So they can ask this thing in one of the option. In case of Newtonian fluid, viscosity is constant. It is not a variable. It depends upon shear stress. It depends upon velocity gradient or rate of shear strain. Like that, they can ask. Okay. So when it comes to non-Newtonian fluid, you see the slope depends upon du by dy, which is your rate of shear strain. So if you are changing, if you are applying more and more shear stress, or more shear strain is there in your fluid, the viscosity will keep on changing. And this is what happens in case of, let's say, if I take example of honey. So if you take honey, initially it is very thick, but what happens if you continuously stir it? Or in case of sugar and water solution, what happens? Initially it will be thinner, okay, not that viscous, but when you are continuously applying a shear stress round and round and round, if you are applying a shear stress between two layers, like fluid will move like this, no? So these two layers are there, so between them there will be a viscosity. So what happens, after sometimes you will feel that it has become very thick, so you will have to apply more effort there. So what happens, the viscosity has increased. So with time the viscosity is increasing. In case of other fluids, it may happen the viscosity will reduce. Like if I take the example of paint, if you buy new paint what we apply over a wall or our any window anywhere. So if you buy a new bottle or new cane, it will be very thick and you cannot apply directly that one. It would be costly also for you. What you can do is, first you should stir it properly. So what happens? It will become thinner. So with time you see the viscosity is reducing. and if viscosity has reduces sufficiently, and then you apply over the wall or over the window, it will flow properly. And if it is flowing properly, less amount of your this paint will be required. Okay, so that is why before applying that paint over a wall, you should stir it properly, and it will reduce your viscosity. So you see the viscosity is reducing also with time for some fluids, it is increasing also with time for some fluid, and it is constant also with time. So are you able to distinguish between these things, these different types of fluid? So the noticeable difference here is for Newtonian fluid, viscosity is constant with time. For non-Newtonian fluid, viscosity is varying with time. Okay, and it depends upon shear strain rate itself. Okay, so we can plot this thing, we can plot here. So non-Newtonian fluid, this is the equation, sorry, in Newtonian fluid this is the equation, non-Newtonian fluid this is the general equation. So you see this is our Newtonian fluid, which is a straight line. Here n value is 1. You see, you apply n equals to 1 here, you will get tau equals to mu du by dy. M will become mu du by dy, and this will become 0. So here this is a linear behavior. Now for dilatant fluid, if n value is is greater than 1, if n value is greater than 1, then what happens with, if you apply this shear strain, no, if you are stirring like this, with the time it becomes thicker. Okay, so we call those types of fluid as shear thickening fluid. And you see the slope, with slope also you can understand the slope is continuously increasing. And what the slope it represents the apparent viscosity. So with slope also, with mathematical proof also, you can say that the viscosity of fluid is increasing with this strain rate. And we call this type of fluid as shear thickening fluid or dilatant fluid whose n value is greater than 1. Okay, then there is one more type of fluid which is shear thinning fluid. So here what happens, you see the slope is reducing continuously. Okay, so with this shear strain the slope is continuously reducing, and n, you see n value is less than 1. Now there are some fluids which initially required some shear stress. Initially it requires some shear stress to start flowing. Okay. If you are not applying this shear stress, it will act as a solid, like cream. It looks like solid. When you apply some shear stress with your finger, it will start flowing. Okay. So those types of fluid requires some initial shear yielding stress. Some yielding stress is required. After that, again, if it is following linear behavior for flow, we call that as Bingham plastic or ideal plastic. If it is this viscosity is increasing with time, rheopectic shear thickening fluid. Thixotropic shear thinning fluid. Okay. Now two more things are left here, which is also important. They can ask, the horizontal line is ideal fluid. Horizontal line is your ideal fluid. Without applying any shear stress, it will start flowing. You see, continuously it will flowing. So you will not notice any, viscosity between the two layers. You see, this is what? Horizontal line. Whose slope is what? Whose slope is what? 0. If flow slope is 0 means what? Is viscosity is 0. So between two layers, there will be no viscosity. And hence the horizontal line is represented by our ideal fluid. And if I come to vertical line, this represents our solid. Why? A infinite amount of this is what vertical line whose slope is what infinite. So infinite amount of shear stress is required to make that solid flow, because in a solid, if you apply a shear stress or shear force, it will not flow. Infinite amount of shear stress will required, and even that then also it will not flow, it will break. Okay, so this is the basic differences between different fluids, and this is how we represent in shear stress and shear strain rate graph. Okay, now can you tell me the corresponding graph in mechanics of solid? Which graph is that? In mechanics of solid or strength of material, you might have studied similar type of graph. Ideal fluid. Ideal fluid, I said that for ideal fluid, you see this is horizontal line. Okay, and horizontal line have slope what? Slope as 0, and slope represents what? Its viscosity. Okay, so for ideal fluid, there is no viscosity between two layers. Viscosity is noticeable between two layers only, no? So in case of ideal, what we call as ideal fluid or ideal flow, when there is no viscosity between, no resistance between resistance of flow between two layers. Okay, and resistance is offered by what? Viscosity. So this ideal fluid is having zero viscosity, and that's why we represent it in our horizontal axis. Clear now? Okay, now you tell me what is the corresponding graph in mechanics of solid or strength of material. There, see, you can uh, with this graph also you can give some logic or logical answer or something like that. Like you see, there we have, here we have what? Shear stress and strain rate graph, and there what we have? Stress strain graph. Because there is not rate of shear strain, there is not rate of shear strain, there is only strain. And on one axis we have stress. So here we apply shear stress to flow. So that's why we have this shear stress on this axis. There we have what? Normal stress. Okay, so there we have stress strain graph. Here we have stress and strain rate graph. Is it clear to everyone? Okay, here we have some examples of this different types of fluid. You can take screenshot of this one or you can write it afterwards. Okay, whatever you like, because they can ask one of this example, they can give and ask what which type of fluid is this, like that. Okay, so the important point what we have studied in last slide is that slope, here it is slope, slope. So slope of curve represent viscosity of fluid in that graph. Okay, and slope depends upon rate of shear strain. Okay, now we have this numericals. This numerical will not solve. We'll have another numerical. So two more topics, and then we'll move to this MCQs. Okay. So small topics only. Surface tension, and then we have this one more property is there, which is compressibility. So that we'll study, and then we'll move to our MCQs. So now you see, before studying this surface tension, we need to look this cohesion and adhesion force. Okay, so what is this cohesion force? It is intermolecular attraction between molecules of same liquid. Intermolecular attraction of between molecules of same liquid. This is cohesion. This you know, and it enables liquid to resist a small amount of tensile stress. Now this line becomes important from your MCQ point of view. Okay, which forces allow or enables a liquid to resist a small amount of tensile stress? We know liquid cannot resist tensile stress, but small amount it can resist. No, so what is that small amount? Because of which property, because of what it enable means it can resist this small amount of tensile stress, is this cohesive force. Because you see, this is one molecule, this is one molecule, and there will be a intermolecular force between these two molecules. Now what is tensile force? If you see this block, in case of your strength of material, if you have this block, let's say, and if you are applying a force like this, it will have some tensile stress develop here. If you are applying this tensile force, it will have some tensile stress develop here. Okay, where from this tensile stress comes? Inside there is a molecule which will not allow to break this complete solid. Similarly here also, in case of liquid, we have some small amount of cohesive force. Okay, which is not that significant compared to solid, but it is significant compared to your gas. Okay, so this cohesive force only allows this liquid to have small amount of tensile stress. So this is the reason, cohesive force or cohesion is the reason. Is it clear? Okay, now next is adhesion. So adhesion is, it means attraction between molecules of liquid and a molecule of solid boundary. So it is a molecule of different type, you can say. Okay, molecule of liquid and between molecule of solid will have this adhesion force, and this enables, so this property also has some special thing. What this enables? It enables a liquid to stick to another body. Like if you have this solid body and if there is a liquid, you might have studied also because of surface tension, if it is rising or there is a depression, it will form convex or concave type of this free surface. So there, why this rise is there? Because of this cohesion, this adhesion force. Okay, because there is one molecule of this solid and there is one molecule of this liquid. Okay, and there is a adhesion force. Adhesion means there is a force, attractive force among these two molecules, and this molecule of solid will try to pull this molecule of liquid towards this, and this will try to rise like this. So you see what is happening, it is trying to stick to the solid body. Okay, so this is the adhesion force, and this is also noticeable where it can also be noticeable in case of fluid flow. Let's say a fluid is flowing over a plate, where it is noticeable. This adhesion force, this is the fluid flow over a, yes, near the plate here. Because of this adhesion only, this molecule is not allowing this molecule to flow. Okay, so it is noticeable here. Then capillary action, there is a capillary action, we'll study this in next slide. So there is a capillary action. This is this capillary action happens because of what? Cohesion and adhesion both. Cohesion and adhesion forces both are responsible for this capillary action. Okay, shall I move to next slide? If you want, you can take screenshots also for this slides. Am I going fast or slow, anything? Okay, if you're facing any problem, please let me know. Okay, now next is surface tension. Okay, next is surface tension. So surface tension, where from this property is coming? See, this is coming because of, see, if I take a fluid in this beaker, okay, and it is having so many molecules here. So the molecule, you see the molecule which is at the surface, the name itself suggests the definition. Surface tension, tension on the surface. It is having a tension over the surface. Okay. So, and you see, the moment this tension thing come, you should remember our cohesive force. You should remember our cohesive force, because cohesive force is responsible for small amount of tensile stress which the fluid can resist. So these two are related. Okay, so I'll explain how this thing is related. Before that, let us understand what happens here. You see this molecule which is equally pulled from all the nearby molecules from all the direction, from all the direction. So net force on this molecule is zero only. Okay, but when I see this molecule over on this surface, molecule on this surface, and I have projected this here from top view, from top view you can see like this. So there will be so many molecules here, so many molecules here, all these molecules are there. Okay, now what happens, you see a molecule which is here, it is being pulled by this molecule in this direction, and it is pulled by this molecule in this direction, and this molecule in this direction, and above this molecule there is air, which is important to note here. Surface tension will occur when two different fluids are there. This is one liquid and this is a air. So both are fluid, and surface tension will happen at the interface of these two fluid. There only it is noticeable. Okay. Even if you have two different fluids, you will have the surface tension here. Okay. So when there is two different types of fluid at the interface, you will have that surface tension. Why? Because there is a difference in the attractive force, difference in that cohesion force. Okay, so you see this molecule will have some cohesive force for due to this molecule. It will have some due to this molecule, but above this molecule it is not having same type of same category of molecule, or them say that same liquid is not there. It has air. Now air molecule will pull it in this direction, which is obviously not equal. There will be a difference of forces. So what happens, because of this there will be a net inward force. There will be a net inward force, and because of this net inward force, what happens, there is a tension developed in the surface. To understand this, we can correlate with this particular example. Let's say initially we have this thread here. Okay, initially we'll have this thread here, and let's say there is no tension in this thread. Okay, negligible tension. Now the moment if I put this weight here on this thread, if I put, what happens, it will take this shape, and there will be a tension develop along this thread. Same thing is happening here. There is this weight is pulled, this weight is pulling this thread in downward direction. There is a net inward force which is pulling this molecule in inward direction. Now where from this tension will come? The tension will come in this thread in this direction like this, because of nearby molecules here. Here also we have some nearby molecule which will this molecule will try to move in this direction because of net inward force, but this molecule will not allow this molecule to move in this direction. So there will be a tension develop among these two, and it is happening at the surface, so we call this as surface tension. Is it clear to everyone? Okay, now this is surface tension. Its unit is force per unit length. Its unit is force per unit length. In terms of energy, can anyone tell me how we can write? Okay. Now there is this surface tension. Now there is one property which is known as surfactance. Okay. What this surfactant does? It reduces the surface tension of liquid. It reduces the surface tension of liquid, and that's why we call our detergents as surf. We use surf for washing. What that surf does is, when you mix that surf with the liquid, it reduces the surface tension of liquid and hence allow the molecule to go inside the pores of your cloth and wash it properly. So the companies, what they are telling, that we have good surf or good detergent, actually they are telling they have good surfactant properties. Okay, so and here also this point anyway I have told you, we speak of surface tension for liquid only at liquid liquid or liquid gas interface. You will have this at liquid liquid interface also, or you will have this at liquid gas interface also. Okay, so if there is a two-phase flow, if there is a, let's say in a pipe there is a fluid flowing, and let's say some part is liquid here and some part is vapor here, some part is vapor here. So what happens, let's say this, if this is vapor and this is the interface, this is liquid here which is settled at the bottom, and let's say this is the vapor. So at this interface you will see this surface tension, because inside this we have vapor, here we have liquid. So at the interface we can see this surface tension force. Okay, so in two-phase flow also you will notice this surface tension. Okay, so they can ask, they can give few examples, and they can ask where you can notice surface tension force. Okay, then one more important point, due to surface tension, see there will be a curved surface like this. Okay, either so one is a concave side, one is convex side. So curved, there will be a curved liquid interface in equilibrium results in a greater pressure at concave side. Okay, on concave side you will have greater pressure compared to your convex side, or obviously it is taking a shape like this, so more and more fluid will come, means molecule will compress here and it will have more pressure here. Okay, so on concave side you will have more pressure compared to your convex side or plane side, or compared to your plane surface. Clear? Is this point clear? This is also important, they can ask this also in objective. In concave side of a fluid, like if this is a fluid and fluid surface, let's say this is completely, this is a fluid. Okay, and if it is taking a meniscus is formed like this, so this is your concave side, this is your concave side, it can have like this also. Okay, so this is your concave convex side, this is your concave side. So concave side of fluid have higher pressure, greater pressure compared to the convex side. Okay, now quickly we'll see these equations for pressure inside water droplet or soap bubble or liquid jet. You must have studied these things. Like for water droplet, this is water droplet of diameter d. The pressure difference, the important thing to be noticed here is that this equation is not only, people usually remember is that P equals to 4 sigma by d. Now what is this P? This is not pressure, this is pressure difference. And what is that difference? Difference between inside of bubble and outside atmospheric pressure. So they can ask how much more pressure is there inside this bubble compared to atmospheric pressure. Then what they are asking? They are asking this P is equals to, because delta P, delta P, which is P minus P ATM, is equals to 4 sigma by D. So they can ask how much more pressure inside the bubble compared to your atmospheric pressure. So what they are asking is P is equals to 4 sigma by D plus P ATM. This is the pressure. Or how much more if they are asking, then all you need to tell only this thing, 4 sigma by D, because they are asking difference only. But if they are asking what is the pressure inside, then you should add this P ATM also. Is it clear? Okay. Now for soap bubble, we have two surfaces. Inside also there is a air, outside also there is air. In case of water bubble, outside only air is there, inside it is liquid. So we have only one interface here, liquid air interface. Here we have two, inside also air, outside also air. So this thing will become two times. This delta P will become two times, and that's why we can form that bubble. Okay, soap bubble. Okay, it is not easily, means it takes some time to break this bubble. Okay, because two times this pressure is there. Okay, means two surface tensions are there acting, which is resisting this thing to break. Okay, now there is a liquid jet. If some liquid is flowing like this, some liquid is flowing like this in this direction, so this liquid jet also, you see outside this liquid, inside it is liquid, but outside this surface surface of the liquid we have air. So at this surface also we'll have this surface tension, and this surface tension, if this surface tension is acting, there will be a delta P. Delta P means, like, you see, if I complete this curve like this, there will be a surface tension over this surface. Okay, and there will be a pressure difference between inside the fluid and outside atmospheric pressure. So that pressure difference can be calculated as delta P equals to 2 sigma by D. Okay, I'm not going explaining much in detail all these things, because means we need to just, because you might have studied all these things. Okay, in gate classes I usually go much in deep, all these derivations and all. Okay, here you I assume you have already studied all these things. Okay, so I will not spend much time in this thing. I will spend time on topics where it is more important. Okay, or concept explanation is more important. And but still, if you feel that I need to explain a few things, you can ask. Okay, I can explain, no problem. Okay, now because of this surface tension only, we can see this insect can sit over a surface, and a pin, if you are uh, 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 means placing this pin over a liquid surface, it will float, it will not sink. If you apply small amount of force, you are breaking that surface tension, which is means the force which is resisting to it to sink. That force you are breaking, and then it will sink. Okay, so how it happens, if you take this pin, this is the pin. Now there is a weight of pin which is acting like this, and you see there is an interface here, and at this interface there will be a surface tension. So the component of surface tension force in vertical direction, this will balance the weight of the pin, and hence it is floating over the surface. Now if you apply small amount of force, this thing will break and it will sink. Okay, and you see, I'll not explain this thing in detail. Only thing, we have studied for sphere. Okay, like we have studied for this delta P equation for a water droplet which is a spherical in shape, or liquid jet which is a cylindrical in shape. Okay, so these two are having some fixed radius. But if you are having some surface or some droplet, liquid droplet, which is not spherical, like let's say this is also a curve, this is a liquid droplet whose one part I am showing here, and this is one of its radius, which is r1, and this curve which is having some other radius, r2. Then how to calculate the pressure difference, this pressure minus atmospheric pressure difference in case of this fluid? So you can calculate this thing with this equation. Delta P is equals to sigma by R1 plus sigma by R2. So in case of our this spherical droplet, this R1 becomes equals to R2, and that's why it becomes 2 sigma by R. In case of our liquid jet, one of the radius is infinite, because this is the one radius and this radius is infinite. So because of that, one will become 0 and you will have sigma by R. Okay, so like that you will have equation here. This sigma by R only. Okay, so like that you can reduce the equation, or this is the general equation for any curved surface. Is it clear? So they can ask this also, this equation they can give, and they can ask how to calculate the delta P. Okay, and then comes this capillarity. So capillarity is the rise of fluid in a capillary tube, rise of fluid in a capillary tube. So now it will rise, and up to what point it will rise? You see, there is this molecule which is a liquid molecule, there is a solid molecule, and there will be a force of attraction between this molecule, and it will try to rise. The liquid will try to rise, but up to what level it will rise? It will rise till the weight of this fluid, balances, sorry, or means balances the surface tension in vertical direction, the component of surface tension force in vertical direction, or the surface tension force in vertical direction balances this weight. Till then only it will rise. Okay, if means it cannot rise more than this component of force, sigma cos theta wala component, and this sigma is acting all over. If I see this top view, it will be like this. So all over it is acting like this, all over. So if I want to calculate the force, surface tension force, it is what, surface tension is what, force per meter. Okay, it is force per meter length. Okay, so over all this length it is acting, which is a surface tension, which is a circumference of this tube. So what will be this surface tension force? This will become what, sigma, which is the surface tension force, multiplied by the length. So length is what, this circumference, which is pi d. Now this is in this direction, but you need to calculate in vertical direction. So vertical direction is what, cos theta component. So this is the surface tension force acting in vertical direction, which is balanced by the weight of the fluid. The weight of the fluid, which is what, density multiplied by volume multiplied by g. So this is density multiplied by the volume. What is the volume? Pi by 4 diameter square is the area multiplied by this height. This is the volume of the fluid multiplied by density of the fluid, and multiplied by g will give us this equation. So you can right away calculate there itself, because this is a cylindrical one. This is a cylindrical one, but they can ask two vertical slit are there. Slit, a plate, like this is a plate, this is a plate, and their gap is W. Okay, like this. Okay, the gap is W, and this is like this, and some fluid is here, which is rising in this direction, and some height is this H. So now how much height it can, uh, it has moved in this direction, you can calculate again with this same concept. Only thing here, when you calculate the weight of the fluid, it is not pi by 4 diameter square, because this is not your circular this thing, circular cylindrical kind of this thing. It is a plate. So the volume of this much fluid, how you can calculate? First you calculate the area multiplied by this height. That area multiplied by height will give you the volume, and then again the g. And this you can equate again with sigma multiplied by, now here you will not have pi d. Pi d is for circular thing. Here it is this width this width plus this let's say the depth whatever they have given in the example, or unit depth also they can give. So you'll have to calculate this circumference. So 2 times the width plus, let's say depth I will take as b, then 2 times w plus b. This will give us the length. Okay, over this length 2 times w plus b it is acting. Okay, and then you can deduce the relation for height rise in case of this type of slit. Okay, so any thing given in the question, you can just follow this basic equation. So upward surface tension force is equated with weight of water column. Okay, clear? Okay, let's solve few questions. Okay, and then we'll again come back to concepts. So you can start answering. So this is rapid only, rapid fire is going on. Quickly tell me the answer. Everyone should answer, huh? One, answer for one. So the answer is, have any, all of you have answered or not? All should answer. Here, how many are there? 11. And how many have answered? Okay. So answer for first is D, because you see this is fluid, cannot be subjected to shear force. Obviously this is not there. Now always expand until fill any container. Fluid is liquid also and gas also. So liquid does not expand to fill the container, so this cannot be the possible answer. But in case of is okay, option has the same shear stress at a point regardless of motion, this also is not correct. Now D option, cannot remain at rest under any action of shear stress. Smallest amount of shear stress you apply, the fluid will start flowing. So it cannot remain at rest. So this is the more appropriate answer. Now next, fluid is a substance which offer no resistance to change of what? At a time you answer one only, huh? Don't answer 1, 2 and 3 like that. At a time one only. So fluid is a substance which offers no resistance to change of shape. Okay, to pressure it offers resistance. You apply this thing, apply pressure, it will offer resistance. It offers resistance to flow also. It offers resistance because you always remember it is fluid. It is not only liquid, it is not only gas, it is fluid. So you should think both way. Okay, now next, answer for third. Sorry, what? See, with change in temperature, this thing, like there is a change in viscosities and all those things. So there is the resistance offer, no? There is a resistance for that also. With change in temperature, the properties will change. And with different this thing, different changes will be there. So the more appropriate one is that only shape. Okay, for practical fluid, answer is D. It has viscosity. Practical fluid have viscosity. It have surface tension, and they are compressible. All practical fluids, they are compressible. Gas you take, it is compressible. Even liquid also, they are by small amount they are compressible. Okay, so they possess all above properties. Now fourth one, with questions also you will learn so many things, don't worry. See, static fluid, it is not ideal fluid. Static fluid means a fluid which is at rest. Let's say this is a fluid, static fluid, fluid at rest. So in case of static fluid, see, you people are, whoever is answering viscosity is nil. Okay, viscosity, you are also correct. Viscosity is nil because obviously when it starts moving, then only we'll notice that viscosity. But it has a property of viscosity there. You'll notice that one when it will start flowing. Okay, but in case of ideal fluid, when it is flowing also, you'll not notice that viscosity. But if you see option D, in case of static fluid, only normal stresses exist. Okay, in case of static fluid, like when you apply a small amount of shear stress, what happens? The fluid will start flowing. So this shear stress will only be noticeable when the fluid is flowing. When the fluid is not flowing, there will be no shear stress. Okay, only normal stress exists, which is nothing but the normal pressure at any point, a normal pressure from all the direction. This anyway I will explain in fluid statics part. When I will start the fluid static part now, this I will explain in more detail. As the question has come, I will just telling you few things about this one. So see, in uh, like in static, this linear deformation, see deformation, C part you are asking, linear deformation will only come when this shear stress will come, because shear stress is mu du by dy, no, and this du by dy, or I can say mu d alpha by dt. So this d alpha by dt only is the deformation. When this deformation will come? When you apply shear stress, or when the fluid is start flowing. When it is not flowing, there is no deformation. So there is not at all a deformation noticeable in static fluid when it is stationary. Okay, and it cannot have zero fluid pressure. Okay, anyway, this I will explain in detail when I will teach you this static fluid statics. No, there I will explain this thing in more detail. Here you can note that the answer for this one is only normal stress. Why? I will explain this thing in fluid statics. Don't worry. Now, next, this one, answered for fifth one. Yes, correct. A fluid is ideal when it is inviscid. Actually, it should be inviscid. More appropriate word is inviscid. Inviscid and incompressible. Okay, next question, sixth one. This one a tricky one. This is a tricky one. Yes, it is continuity equation. All fluid, whether it is ideal or practical, it should follow continuity equation. Okay. See, Newton's, if it is ideal flow, Newton's law of motion, or this Newtonian this thing fluid, or Newton's law of viscosity, only this Newtonian fluid follow this Newton's law of viscosity. But ideal flow does not follow this Newtonian law of viscosity. Any fluid should follow this thing. This is the basic thing, continuity equation. Okay, whether it is ideal flow, viscous flow, inviscid flow, compressible, incompressible, whatever it should always follow continuity equation. Okay, now next, seventh question. Okay, answer is ideal fluid. No resistance is encountered by displacement by ideal fluid. Gas can have, there is a resistance, no? That's why in gas also we have that boundary layer formation, no? So viscosity is there, so resistance is there. Okay, so in fluid, any fluid, general fluid, there will be a resistance. Water, it is a fluid only, resistance will be there. Gas, resistance is there. Solid, resistance is there. Only in case of ideal fluid, there is no resistance. Okay. 14th, this is easy one. Property of fluid by which own molecules attracted, it is a cohesion force. It is a easy one. Next one, 15th you can tell. Okay, so uh, if I take any other example, let's say water or any fluid, if I take other fluid, if I take, and if it is wetting the surface, if it is wetting the surface, so it will have cohesive force and adhesive force will not be there. Wetting and not non-wetting of fluid, wetting and non-wetting of a fluid, whether it will form like this or it will form like this, uh, above like this or like this, whether it is wetting or non-wetting, in either of the cases, how we explain this thing? in this case we explain that adhesive force is more than cohesive force, correct? And here we explain that cohesive force is more than adhesive force, correct? So it possesses both thing, both they are having adhesion and cohesion, both. Am I right or not? How we explain this thing, whether it will wet or not? It will wet the surface. What you are telling? Yes. So you see, this is here we explain that there is a adhesive force between this molecule and this molecule. The force is more compared to cohesive force, and that's why it is rising. And here the cohesive force is more. This cohesive force is more compared to this and this molecule. That's why it is dipping. So this force, adhesion and cohesion exists there. So, but which property, because of which property it is not wetting, is this surface tension property. Okay, there is the difference between these two, because of which it is rising or dipping. Okay, but because of surface tension it is either wetting or not wetting. Okay, surface tension will try to rise it like this, surface tension will try to pull it like this. Okay, pull the fluid in downward direction here. Here it will try to pull it upward direction here. Okay, so the answer for this one is surface tension. Okay, this one. I have told you in a single sentence this thing, so nobody should answer this thing wrongly. No one should answer this question as wrong one. Okay, I have explained this thing. Did you get your answer? Okay, so the answer is C, cohesion. Okay, because of cohesion, cohesion is a property of fluid which enables it to resist tensile stress. Okay, next 17. Answer is A, no doubt. Okay, now 18. This is a general thing, general knowledge thing. 18th one. Specific weight of water is 1000 kg per meter cube. Density of water is 1000. At what? At normal pressure 760 mm, 4 degrees centigrade, and at mean sea level. So the answer is D, all of the above. Okay, it is at mean sea level, 4 degrees centigrade, and normal pressure. Okay, normal atmospheric pressure. So the answer is D. Okay, shall I move ahead? Okay, next 20. Although few things may come in between, which I have not uh, explained you till now, but you should be able to answer because these few things are general things. So there is two parameters. Okay, there is a XYZ or XYZ direction or space, what we call as space, and there is a time. Okay, so properties if properties if it is changing with time at any point, see, either one you will have to fix and other will change. So if time is changing, so you'll have to focus at any point. So with time, if at any point property is not changing, it is steady or unsteady. If it is changing or not changing, then depending upon that, it is unsteady or steady. And if you are fixing a space, sorry, fixing a time, like at any instant, and then you are noticing in a flow at different points, like at different points you are noticing, fixing a time. Now you are fixing the time and noticing at different location, then this will tell you whether it is uniform or non-uniform. Okay, this will tell you whether it is uniform or non-uniform. So the answer here, at any given instant, so you are fixing a time and checking at different points whether the property is changing or not, then it is whether it will be uniform or non-uniform. So the answer for this one will be D. Okay, because you are checking at any given instant at different point. Okay, fixing time means whether it is not steady unsteady. Okay, when time is changing, then only it is steady unsteady at any given point. Here it is ulta, fixing time and checking at different points. Okay, like here also velocity is 10, here also 10, here also 10, here also 10, here also 10. So it is uniform. Okay, if it is here 10, it is here, it is, let's say, 20 at given instant, two different velocities, so it is not a uniform velocity. Okay, like that. Yes, steady means whether it is with time property is changing or not changing. That anyway I will explain when I will start this fluid kinematics. No, I will explain this also. This thing, these general things are coming in between. You should know. That's all. This is your test. This is your general test, whether you have understood those basic things or not. Okay, I will explain these things anyway. 21. Okay, so no doubt it is specific gravity. Okay, 22. Okay, for 22 it is at rest. So normal stress in a fluid will be constant in all direction at a point only if it is at rest. So similar question we have seen in previous slide, I think, or last to last slide. So in other way they are asking, in जो घुमा के पूछ रहा है, nothing else. Okay, next. See, pressure at a point in a fluid will not be same. Obviously, when it is moving, it will not be same. Okay, but if it is viscous also, see, if it is viscous also fluid, then also because viscosity comes into picture when it is moving. Okay, so viscous case and moving. Okay, viscous and moving, then only you will find that pressure is not same in all direction. Okay, viscous and moving wala case, then the pressure is not same at same in a fluid in all the direction. Okay, when the fluid is static, then only at any point it is same from all the direction. Okay, next 33. Not viscous and moving, you are asking. Not viscous and moving, then also it is moving, no? So pressure anyway, it will be means it will not remain same, no? Means at any point it is moving, no? That fluid. Actually, this is debatable only because you are right. Means this also is correct in viscous, inviscid, but moving. Then in that case, moving, so in moving wala case, this thing is not same. But okay, this I will let me first explain you this fluid statics. Okay, then I will there itself I will just explain this thing because this is a part of fluid static wala part. So this anyway I'll explain there. Don't worry. Where next topic is fluid static only. There I will explain. You just remember remind me that part. Okay. Few things are coming in fluid statics only. Let me just check till surface tension only we will just complete. Okay, this 40 and 41. 40 to you may be knowing. Okay, tell me 40. It is a Newton per meter. Okay, 41. Okay. So surface tension, where this thing acts, surface tension. Okay. So wherever, like if we have, this is air and this is liquid, so at this interface only we'll have this surface tension. Okay, so if we see from top view, this is the plane. From top view, if you see, this is a circular thing, so this is the plane and surface tension will act like this. Okay, so where it is acting, so it acts in a plane of interface which is normal to any line of the surface. Obviously this is not there. Next, it is function of curvature of the interface. See, it is not function of the curvature. Curvature forms because of the surface tension, because of the cohesion and adhesive force difference. This curvature will form. Okay, and because of surface tension it will either rise or it will dip, but because of the surface tension, this thing happening. Okay, so it is because of the surface tension this curvature will form. So it is not the function of this thing. Okay, curvature, not a function of curvature. Because of curvature, surface tension is not forming. So this option is also not correct. Now surface tension, if you increase the temperature, surface tension increases. Okay, if you decrease this temperature, it may, with temperature it depends, it may increase or decrease. Okay, means not may increase or decrease, marginally only it increase or decrease. Okay, so the effect that it is there with surface tension, that effect of temperature, it is there. Okay, so this option can also be considered as correct. Okay, like because surface tension will reduce if the temperature decreases. Okay, and if the temperature is increasing, the surface tension, oh sorry, ulta I have said, if the temperature increases, the surface tension reduces, or if temperature reduces, the surface tension will increase. But here what it is telling, it is telling you the ulta thing. Sorry for that last statement. The surface tension of any fluid, if you if you are washing your cloth, people usually tell that in warm water you should close your if you should wash your cloth. Why? In that case the surface tension of water will reduce. If the temperature is increasing, the surface tension of water will reduce, and hence it will enter the pores in a better way compared to your cold water. Okay, so temperature increases, surface tension decreases. Temperature reduces, surface tension should increase. Here it is written that if it is decreasing, this also will decrease. So this is also not right, and this is also not right. So the option for this one is A. Okay. And how much it increase or decrease, it depends upon the temperature, but marginally only it increases or decreases. Okay, those things you will get with value. Okay, 42. So stress strain relation for Newtonian fluid, I have told you it is linear. Linear. Okay. Next, 43 you can tell. Anyone is facing any problem? Yes, you are right. It should be stress versus strain rate. Correct. You are right. Stress versus strain rate relation. Anyone is facing any problem? Any feedback? If you want any improvement, anything, you can let me know. Next class, I will do that for you. Okay. But my target is in this fluid mechanics, these type of MCQs will try to solve at least 400 to 450 questions will try to solve. Okay, so just try to stick with these classes. Okay, I'll try to solve. Today my target was around 100 questions, but okay, little bit slow we went, but next slide I will try to move little fast. Okay, we have target to solve at least 450 question. You are ready now for 450 questions in complete fluid mechanics? Okay, 43rd. Okay, this I have not taught you. I think this I have not explained. Bulk modulus of elasticity. Actually, that is next topic only. So okay, you can skip next class. We can solve this question. It is easy equation only. No problem. Next class we can solve that one. Huh. This you can tell. 44 and 45. Easy one. 44. First 44. I need 44. Yes. Unit of viscosity is what? Pascal second. What is Pascal? Newton per meter square second. Now, Newton can be written as kg meter per second square. Then multiply by 1 by meter square, multiply by second. Okay? This cancel out. This. What is the unit? Kg per second and then meter. Is this the unit? Pascal second. Pascal second only, no? Second square per meter square. And this only should come. Or Newton second per meter square, like that also सी ही हो जाएगा. Yes sir. Yes. इससे ही हो जाएगा. Okay. इससे ही from here itself. I thought I was deducing this one whether this is also correct or not. Okay. Next 45. Yes, it depends upon density. Okay. Kinematic viscosity. Mu by rho. Mu by density. Okay. This one. 5 more minutes. Can we go? 5 more minutes. We'll try to solve 4-5 more questions. Okay. So 46. Surface tension. Surface tension is force per unit length. So Newton per meter. Or if we multiply, I have at that time itself I've asked in terms of energy. So if I multiply by meter and divide by meter, it will become like this. And Newton meter is what? Energy by area. So what can be the answer? Energy per unit area. Okay. Okay. 54. The property by virtue of which it offers resistance to shear. It is which property offers resistance? Okay. So viscosity, obviously. Okay. Viscosity is the property which offers resistance to flow or shear this shear stress. We apply shear stress and see tau equals to mu du by dy. We apply this shear stress, say there is a deformation, it resists this shear stress or deformation by virtue of this property which is viscosity. Okay. So today we'll end here, and in next class one or two more properties are there, fluid properties, that will complete, and then we'll try to complete fluid statics. Okay. And then we'll try to solve around 50, 60 or 100 questions, around at least 50, 60 questions of this thing, fluid statics also. Okay. And if you need any improvement, anything is required, you just let me know. Okay. Thank you. Good night. At last I will tell you. Don't worry. I will give this MCQs now. Later I will give you. It is better to solve in class now these questions. If you have any doubt here itself, it will get resolved. Okay. I will end the meeting now.